Section: Introduction. In this section, we discuss synthetic data generation, which involves creating data through algorithms, generative models, or simulations instead of human input. This method is particularly useful for training models when real-world data is limited, costly, or hard to access. We explore various techniques for generating synthetic data, including using advanced teacher models to train smaller student models. For example, a recent approach involved using ChatGPT to create a high-quality chat corpus by having it converse with itself. We also examine how a model can generate its own high-quality synthetic data to enhance its performance. The Self-Instruct framework allows a language model to use a few examples to create new synthetic data. This data can then be used for self-training, as seen in the self-rewarding framework. Instruct takes this further by increasing the complexity of prompts, allowing the model to rewrite them. Other methods for generating complex synthetic data include multi-hop question answering and challenging reasoning tasks based on documents. Additionally, synthetic data has been utilized for training agents and tool use models. Our approach, called Chain of Thought, CoT-Self-Instruct, focuses on generating high-quality synthetic data through reasoning. We start with access to a language model and a small set of high-quality human-annotated seed data. Our method consists of two stages. 1. Synthetic instruction creation with Chain of Thought, CoT. We take sample seed instructions and prompt the language model to reason step by step to create new instructions of similar complexity and domain. 2. Synthetic instruction curation. We then refine the generated synthetic data, keeping only the high-quality instructions for self-training. In the first stage, we begin with a small pool of seed instructions. We randomly sample multiple instructions and use them to prompt the language model to generate intermediate reasoning steps, leading to a new instruction. Unlike standard methods that directly ask the model to create new instructions, we first have the model analyze the seed instructions for their domain, complexity, and purpose. After this analysis, the model reasons through a plan to produce a new instruction that matches the quality and complexity of the seed instructions. For verifiable reasoning tasks, where we can compare answers to generate rewards during training, we instruct the model to create both an instruction and a verifiable target. For general instruction following tasks, we only ask the model to generate the instruction, not the response. During training, we then use a reward model to evaluate the responses, which removes the need for a reference answer. To ensure quality, we categorize seed prompts before sampling, as mixing prompts from different domains can lead to unnatural results. In the second stage, we curate the generated synthetic instructions, as not all of them will be well-defined or effective for training. We implement a filtering method called answer consistency to retain only high-quality data. For each task instruction, we have the model generate multiple responses and select the majority. If this majority response does not match the target answer, we discard that example from the training pool. This method provides an additional layer of filtering, as the target answer is derived from extensive reasoning steps, making it potentially more accurate than responses generated during inference. Our experiments confirm that answer consistency outperforms standard filtering methods. Section Summary. In this section, we explore synthetic data generation using advanced language models to create high-quality training data from a small set of human-annotated instructions. Our approach, CoT-Self-Instruct, involves generating new instructions through step-by-step reasoning and curating the output to ensure only high-quality data is used for self-training, enhancing model performance in both verifiable reasoning and general instruction following tasks. Section: Self-training with synthetic data. In this section, we discuss our approach to self-training using synthetic data. After generating our synthetic training data, we train an instruction following model based on these instructions. We evaluate the performance of our self-trained large language models, LLMs, against models trained on human-annotated data and initial instructions in both reasoning and non-reasoning areas. For tasks requiring verifiable reasoning, we utilize a method called GRPO, and for general instruction following, we consider both offline and online DPO, which tend to perform significantly better. We examine the effectiveness of our synthetic prompt generation method across reasoning and non-reasoning domains, focusing on two main aspects: how we generate synthetic prompts and how we curate them. For our seed instructions, we use a set of 1,000 diverse and challenging reasoning tasks known as S1K. From this dataset, we filter out theorem-proving questions to keep 893 verifiable reasoning instructions that yield simple, easily verifiable answers, such as single numbers or straightforward expressions. This filtered set serves as our seed pool for generating additional verifiable reasoning tasks. In terms of prompt generation, we apply the CoT-Self-Instruct template and compare it to our baseline self-instruct method. We test these methods on various Qwen 3-4b models, adjusting parameters like temperature and top p-values for optimal performance. For instance, when using the Qwen 3-4b base model, we prompt it with two randomly chosen reasoning questions from our verifiable set, instructing it to create a new reasoning question without any reasoning process. In contrast, when using the CoT-Instruct template, we guide the model to reason step by step before generating a new question. We also explore different configurations of the Qwen 3-4b model, such as using it in think mode or no think mode, to see how these settings affect the generation of reasoning questions. In think mode, the model reasons through the instructions before producing a question, while in no think mode, it generates a question directly without reasoning. For our reinforcement learning experiments, we employ GRPO training, starting from the Qwen 3-4b base model and using rule-based verifiable rewards. We set specific hyperparameters, including a learning rate schedule and the ADAM-W optimizer, and conduct our training over 40 epochs with a batch size of 128. We sample multiple rollouts for each prompt to ensure robust performance, using verifiers like Virl and MathVerify. Additionally, we establish baselines for our self-instruct and CoT-Self-Instruct methods by training on the original S1K prompts instead of synthetic data. We also compare our results with training on the Open Math Reasoning dataset, which contains 10,000 prompts with publicly available solutions. We investigate various methods for filtering data and constructing targets, including self-consistency filtering, RIP filtering, and best of K targets, to enhance our main experiments. Section Summary. In this section, we describe our approach to self-training and instruction following model using synthetic data generated from a curated set of reasoning prompts, specifically focusing on verifiable reasoning tasks. We evaluate the effectiveness of our synthetic prompt generation methods against human annotated data and explore various configurations of the Qwen 3-4b model to enhance the generation of new reasoning questions. Section: Evaluation. In this section, we evaluate our methods using datasets like Math 500, AMY 2024, AMC 23, and GPQA Diamond. We set the temperature to 0.6 and top P to 0.95 for generating predictions. For prompt curation, we explore several methods. First, we use a self-consistency-based filter, where we calculate the ratio of majority-voted answers to total votes and filter out prompts with low self-consistency. Next, we apply a RIP-based filter, where we annotate responses to compute scores based on the lowest score, response length of the lowest scored answer, and the score difference between the highest and lowest responses. We also implement an answer matching filter, where we curate prompts based on majority-voted answers matching a reference answer generated during the CoT-Self-Instruct phase, as this reference may be more accurate due to its reasoning process. For our seed instructions, we utilize the WildChat RIP filtered by -8b Llama dataset, which contains 4,000 high-quality prompts filtered from 20,000 raw prompts across various domains. To avoid unnatural prompts, we categorize the seed data into 8 distinct categories and select 2 prompts from the same category for few-shot examples. These categories include writing and storytelling, technical and programming, creative and design, data and analysis, education and research, communication and support, business and marketing, and miscellaneous. In prompt generation, we compare CoT-Self-Instruct with baseline methods using the Llama 3.1 to 8b Instruct model. We present the CoT-Self-Instruct template and the baseline Self-Instruct method, along with a shorter CoT version for comparison. To filter synthetic prompts, we use the RIP method, which proved more effective than a reward model we tested. We generate 32 responses for each synthetic prompt and have Athene rate them, calculating the RIP score based on these ratings. We control the length of CoT prompts by using different templates. A no-CoT template generates prompts directly, a short CoT template uses a brief reasoning process, and a long CoT template employs a more extensive reasoning approach. For DPO training, we start with the Llama 3.1 to 8b Instruct model, using a batch size of 64 and a learning rate of 1/1,000,000. We generate 64 responses for each prompt, which are annotated to select pairs. Our synthetic prompts tend to be more complex than human prompts, leading to longer responses. To address this, we combine reward scores with length information to prefer shorter responses when scores are similar, applying a length normalization coefficient of 0.2. Our synthetic prompts outperform the original WildChat prompts in DPO training, showing improved performance as the length of CoT increases. Section Summary. In this section, we evaluate our methods using various datasets and explore different prompt curation techniques to enhance synthetic reasoning prompts. We utilize a structured approach to generate and filter prompts, ensuring high quality through methods like RIP, and demonstrate that our synthetic prompts outperform original ones, particularly as the complexity of the prompts increases. Section: Online DPO Training. In this section, we evaluate online DPO training by following the specified training settings. We utilize default sampling parameters, generating exploration rollouts with a temperature of 1 and a top P of 1. Our models are trained using the FAIRSEQ2 library, and we perform model inference with the VLLM library. Our main findings are summarized in two tables, one for reasoning tasks and another for non-reasoning tasks, with additional variations and details in the appendix. We observe that synthetic instructions created by CoT-Self-Instruct outperform those from Self-Instruct. Specifically, in the reasoning tasks table, the Qwen 3 to 4b base models trained on prompts and responses generated by Qwen 3 to 4b show that CoT-Self-Instruct achieves an average accuracy of 53.0%, while Self-Instruct reaches 49.5%, both without data filtering. Similar trends are noted when using Qwen 3 to 4b base generated targets. When we apply filtering methods to both CoT-Self-Instruct and Self-Instruct, we find that both methods improve, even though the total amount of training data decreases. This indicates that high-quality synthetic data is more beneficial than a larger quantity of lower-quality data. Notably, CoT-Self-Instruct retains its advantage over Self-Instruct regardless of the filtering method used. For instance, with self-consistency filtering, Self-Instruct improves from 49.5% to 53.6%, while CoT-Self-Instruct rises from 53.0% to 55.1%. We also find that the best filtering criterion is to exclude prompts with RIP scores below 50%. In our experiments, training the Qwen 3 to 4b base model on self-instructions generated by prompting the Qwen 3 model to reason step by step yields an average accuracy of 53.0%, comparable to the 53.4% achieved with CoT-Self-Instruct templates. Furthermore, filtered CoT-Self-Instructions using self-consistency and RIP filtering methods outperform unfiltered instructions. By applying consistency filtering, we enhance the model's reasoning performance, improving accuracy from 49.3% to 52.2% for Self-Instruct and from 53.6% to 54.5% for CoT-Self-Instruct. We also observe that filtering out both lower and higher consistent instructions can further enhance performance. For self-instructions determined by the highest scored model response, RIP filtering boosts average accuracy from 53.2% to 56.9% by excluding instructions with lower 25% quantile RIP rejected scores. Additionally, filtering out prompts with shorter rejected responses improves performance from 43.8% to 44.3%. Finally, we find that high-quality synthetic prompts generated by CoT-Self-Instruct significantly outperform seed instructions and other publicly available reasoning prompts. Models trained on 2,926 filtered CoT-Self-Instructions achieve an accuracy of 57.2%, which is much higher than the 44.6% from S1K prompts. Even when we filter CoT-Self-Instructions to match the training size of S1K, we still achieve 54.2%. These results also surpass those obtained with 10,000 open math reasoning instructions, which yield 47.5%. Increasing the CoT-Self-Instructions with answer consistency filtering to 10,000 further improves results to an average of 58.7%. Section Summary. In this section, we assess online DPO training using default sampling parameters and the FAIRSEEK2 library, revealing that CoT-Self-Instruct consistently outperforms Self-Instruct across various reasoning tasks, particularly when high-quality synthetic data is prioritized through filtering methods. Our findings indicate that applying filtering techniques enhances model performance, with CoT-Self-Instruct achieving notable accuracy improvements compared to both unfiltered and lower-quality instruction sets. Section. CoT-Self-Instruct then answer plus answering matching filter achieves the best reasoning performances among all CoT and no CoT curated self-instruct methods. In this section, we demonstrate that the CoT-Self-Instruct then answer combined with the answering matching filter delivers the best reasoning performance among all CoT and no CoT self-instruct methods. As shown in our results, when we train the Quen 3-4B base model using self-instructions generated by prompting the model to reason step by step, we achieve an average accuracy of 53.0%. This is comparable to the 53.4% accuracy obtained using the CoT-Self-Instruct template with the same model. Additionally, applying the answer matching filter enhances performance significantly, increasing accuracy from 53.0% to 57.2% by filtering out 40% of the CoT-Self-Instructions. We find that the high-quality synthetic prompts generated by CoT-Self-Instruct outperform both seed instructions and other publicly available reasoning prompts. Specifically, models trained on 893 consistency-filtered CoT-Self-Instructions achieve 50.9%, which is notably higher than the 44.6% from S1K prompts and the 47.5% from 10K open math reasoning instructions with gold labels. The self-instructions from the CoT-Self-Instruct then answer template, combined with answer matching filtering, further enhance performance, achieving the highest reasoning results compared to synthetic and seed instructions. For non-reasoning tasks, we observe that allowing the model to create a plan in advance using CoT-Self-Instruct significantly improves the quality of synthetic data. Averaging results from Alpaca Eval 2 and Arena Hard, we achieve 53.9% with CoT-Self-Instruct compared to 47.4% with Self-Instruct, both without filtering and training with DPO. We also note that longer CoT reasoning chains yield better results than shorter ones, highlighting the importance of reasoning in generating synthetic data. Furthermore, applying the RIP filter enhances the results of CoT-Self-Instruct, increasing performance from 53.9% to 54.7%. The RIP filter also benefits Self-Instruct, raising its performance from 47.4% to 49.1%, although it still lags behind CoT-Self-Instruct. We can also apply RIP filtering to human prompts from wild chat, resulting in a more significant boost from 46.8% to 50.7%, likely due to the noisiness of human data compared to synthetic data. Our best-performing model, trained with DPO, utilizes CoT-Self-Instruct with RIP data filtering, achieving an accuracy of 54.7%. This surpasses the performance of Llama 3.1 to 8B Instruct at 27.1% and human prompts from wild chat, which score 46.8% without RIP filtering and 50.7% with it. We also conducted experiments with online DPO, which further improved results, with human prompts from wild chat reaching 63.1% and CoT-Self-Instruct with RIP achieving 67.1%. Overall, we conclude that CoT-Self-Instruct with RIP filtering provides the best performance across all tested datasets and synthetic data generation methods.